Hello aspirant. This question is from GATE 2021, Mechanical Engineering paper, Set 1, question number 19. The shear stress distribution on cross-section of the coil wire in a helical compression spring is shown in the figure. This shear stress distribution represents option A, direct shear stress in the coil wire cross-section, option B, torsional shear stress in the coil wire cross-section, option C, combined direct and torsional shear stress in the coil wire cross section, or option D, combined direct shear and torsional shear stress along with the effect of stress concentration at inside edge of the coil wire cross section. So given spring, it's a helical compression spring, that it is open coiled, and second thing to be noted is that it resists axially applied compression or the compressive force that is applied along its axis. To visualize it better, let me explain this with a diagram. So if this is the spring that you have and this is the axis of the spring, compression is applied along the axis. I haven't shown any support in any of the ends. I have shown the compressive forces on both sides so that there will be an occurrence of the deformation. If I show only on one side, the spring will not deform, it will move and there will be motion of spring and not deformation of spring. Here we have two entities to note. First one is the diameter of this turn. Let's call it capital D. So capital D is the mean diameter of coil. And another diameter is of this wire, the wire of which the spring is made of, or the wire that is twisted to form this spring. So if we just take an arbitrary section anywhere on the spring, we'll get to see a cross section. That cross section is also circular. This represents that little cross section of the coil wire. Let the diameter of this be small d. We have small d is coil wire diameter. So this is mean diameter of coil itself and this is the coil wire diameter. Now, if we let this compression be P, how is the wire cross section affected? Let's study that. So, the wire cross section will resist this load P by producing a reaction P. Let's say we are looking at this spring from the top. We will see this coil whose diameter will be capital D. And this force is actually being applied at this center point. In this case, if we are looking from here, we can see the force inwards towards the screen. So wherever the section lies on this coil, it will be at a distance d by 2. This distance is half of the diameter, so it is d by 2. And that is why this will always be subjected to a torque P into d by 2. And P into d by 2 will be clockwise to this section. So the section will resist this clockwise torque by giving a anti-clockwise reaction. And this torque will be Pd by 2. Now this resistance P will be uniformly distributed throughout the area in terms of direct shear stress, while this torque Pd by 2 will be distributed on the cross section in the form of torsional shear stresses. So direct shear stresses due to the resistance to compressive load P and torsional shear stress due to the resistance to torque. Let's now look at the distribution of these two stresses along with their combination. Let's see one by one what stresses these forces are going to produce. So first we will see the stress due to this compressive force P, which is given by tau D is equal to P upon area. Now this direct shear stress is assumed to be an average value constant throughout the diameter. So we have it to be force per unit area, that is P upon pi d square by 4, which is equal to 4P by pi d square. Its distribution will be uniform throughout the diameter. So we can draw it like this. Now this torque is also acting in the plane of the cross section or tangential to the cross section. So this will also produce shear stress. Value of that shear stress will be found out from torsional equation. So we can say due to torsion is equal to torque T upon J into radius R. This is from the torsional equation T by J equal to tau by R, where tau T is torsional shear stress. Just putting the value of torque as PD by 2, J as pi by 32, D to the power 4, and R value we will put to be D by 2, because we will find the value of stresses at extreme points, at the extreme inside edge and the outside edge. So distribution of this shear stress will be given as extremes at this edge. The torque direction is like this. So the effect of shear stress should actually develop a torque in anti-clockwise direction. So we are giving a positive stress on the right side and negative on the left side. And just joining these two. 0 at center, of course, it is symmetric. This is the shear stress distribution due to the torque PD by 2. Now the actual shear stress that is developed in this coil is nothing but a combination of these two. So let's plot the combination of these two. On the right side, we add the ordinates. So we will get an even higher value of stress, while on this left side, direct shear ordinate is subtracted from the torsional shear ordinate. And so we have a smaller stress value, and distribution that we obtain here is of this fashion. So the neutral axis or the neutral point has shifted towards the left because this value is smaller now and this is higher. So the shear stress distribution that is given in the question is of this fashion. But there is also a fourth option given which talks about the stress correction factor on inside edge. So the inside edge will have a higher stress value. This is the inside edge, this is the outside edge. You can check in the spring diagram. When a correction factor is applied to this inside edge due to the curvature effect, because spring is given turns, and due to these turns the inside length is smaller than the outside length, and because of which the inside stress will be higher. There will be a stress concentration in the inside edge, and to account for this, various correction factors are applied, and the resulting stress distribution after applying the stress concentration factors, the distribution of shear stress will no longer remain linear. This value will be even higher. Obviously, we do not decrease the stress value ever, because we have to be on the safe side in design, and so for safety reasons, stress value is never reduced. These correction factors are always greater than 1, and hence the stress value will increase only on the inside edge, while on the outside edge it remains the same, and we have a distribution somewhat like this. But the shear distribution diagram that is given to us is this diagram with a linear distribution, and so our answer is option C. Option A is giving this direct stress alone, option B is giving the torsional shear stress alone, C is giving their combination with a linear distribution, and D is telling us to incorporate the effect of stress concentration factors. So the distribution that is given to us in the diagram in question is corresponding to option C. Hence our answer is option C. For more details on various types of springs and the shear stress developed in the springs, you can refer to the NPTEL video lecture 40 Springs 2 lecture series on strength of materials by Professor S.K. Bhattacharya, Department of Civil Engineering, IIT Kharagpur. I hope this explanation will help you clear your doubt. Thank you.